Welcome to 1D kinematics. Now that we have derived the 5 equations of kinematics in the last lesson, today we are going to practice using those 5 equations. So, let me see if we have, I'm going to go back, scroll back to the beginning of the last lesson, and I'm going to revisit those 5 equations that you're going to be using. So here they are. There's the 5 equations. And so we're going to be referring to that on and off throughout this lesson, okay? So, back to our page. How do you solve when you have a constant? Those 5 equations of kinematics are all applied for constant acceleration problems. So the first step you should always do is draw a diagram. Write out the values you know and identify which values you need to solve for. Make sure you're looking at what's positive and what's negative directions. And then choose an equation from your list of possible equations that involves what you know and what you are solving for. So let's try this out. A motorcycle travels west, increasing its speed from 6.5 meters per second to 9.2 meters per second through a distance of 48 meters. What is the motorcycle's acceleration? Okay, so let's identify some things here. First off, it's traveling west, okay? And it starts, the initial velocity, v1, would be 6.5 meters per second. Now notice this is not an average velocity, these are instantaneous velocities. So the initial velocity is 6.5, v2 would be 9.2 meters per second. And then the distance it travels is 48 meters. And since it says it's traveling west, we're assuming that the direction is not changing, okay? And it asks, what is the motorcycle's acceleration? And so what we are looking for, and I'll highlight that in a different color, is acceleration. Okay, so let's see how we solve this. So first we draw a diagram. So we have V1, we have a motorcycle, right? Drawing that, and it's heading west, and we're saying that west is positive. And V2 is 9.2 meters per second west. Our displacement, or change, is 48 meters west because it's heading west, so that means it's going to be moving further west. Okay? And so we have V1, V2, delta D, and it's looking for A. Okay? Using the 5 equations of kinematics. So you look at the equations, and let's go back to, let me see if I can go to pictures. Oops. If we look at our 5 equations, remember we have V1, V2, we're looking for A, and we have delta D. So which ones do that? So equation 1 has delta T, not delta D, so we don't want that one. Equation 2 has delta T, and we don't have, nor do we need delta T, so that's not one that we want because we're looking for acceleration. Again, 3 has delta T, so we can basically eliminate 1, 2, 3, and 4 because all of those have delta T, and we don't have delta T, nor are we looking for delta T. So we're going to go to the 5th equation. So V2 squared is equal to V1 squared plus 2A delta D. So if we go back to notability, that's the equation that we're going to use right here. And so now we plug in the values now that we know. How you can do it one of 2 ways. You can plug in the values here and then solve for delta A. Solve for the acceleration. Or you can manipulate this equation to solve for A, and that's what they did here. So to get A by itself, we need to subtract V2. Let me change that color. We need to subtract this and move this over to the other side. So by subtracting V1 squared from both sides, we get this equation right here. V2 squared minus V1 squared is equal to 2A delta T. And we want to get A by itself. So now we're going to divide both sides we need to divide by 2, and we also need to divide by delta D. So we're dividing both sides by that. So here, when we divide this side, so So we can divide both sides by 2 delta d, divide this side by 2 delta t. And what you end up getting, it's a little bit messy. So what you end up getting is v squared minus v1 squared, v2 squared minus v1 squared, divided by 2 delta d. And that equals our acceleration. So now we just plug in. We got 9.2 squared minus 6.5 squared over 2 times delta d is 48. And that results in 0.4416 meters per second squared, which is our acceleration. You can round this if you used significant figures. You would find that the acceleration, you can just round to 2 digits, 0.44 meters per second squared west. Make sure you're subbing in positive or negative signs indicating direction. Both of ours, since we said west was positive, both of them are positive, and we ended up with a positive result. So the acceleration was in the westerly direction. Okay, here's example number 2. After 5.2 seconds of uniform acceleration, so uniform means constant. So that means we can use our kinematic equations because those involve constant acceleration. So here we have a time, 5.2 seconds. We have a delta t as 5.2 seconds of uniform acceleration from rest. A spacecraft reaches an altitude of 5.7, it's going up, times 10 to the 2 meters up. So what is the final velocity of the spacecraft? So it's asking for the final velocity. What is the acceleration of the spacecraft? Okay. And here's another piece of information that we're given from rest. You need to look for those keywords. From rest means that we know that the initial velocity, so v1, is 0. So if we look over here, here's our diagram. We have it's initially 0. Here we don't know what this is. We know the time is 5.2 seconds. We know the displacement is 5.7 times 10 to the 2, 10 squared. And so here we have all these, and we're looking for these two things. So we're probably going to have to do it in 2 different steps. Okay, so here, when we solve for v2, we have our delta d, which we have our delta t, and we have that, and we have our v1. So we can plug in that equation and solve for v2. We're looking for, and we can do that. This is what we're looking for. So if we arrange this equation algebraically, so that means over here, we're going to multiply this by 2 to get rid of the 1/2. So here we'd have 2. That's where this 2 comes from. And then we would divide, because we want to, by delta t. That way these can cancel, right? Delta t. So we end up with, I'm going to erase it now. So we end up with 2 delta t divided by, 2 delta d divided by delta t minus, and then we have to, after we have to subtract out our v1. They should have done this in 2 steps. It's a little bit confusing in doing it in your head. And that equals v2. So if we plug everything in, we end up getting to our 19.23 meters per second is v2. Now, what is missing here? We know this is in a positive, this ends up being positive, right? And so what would the direction of this be? The direction, they should have labeled this, that this was up. Because a vector has to have a magnitude and a direction, and they didn't give us the direction, so that should be up. I don't know, my iPad's glitching. Okay, so now that we have that, now we can solve for acceleration. So we have our delta d, and we can use this equation, right, to solve for the rest. Since we know that v1 is 0, we can just cross out this whole term right here, because that's all going to be 0. So now we have, this makes it pretty simple. We have delta D is equal to 1/2 AT squared. And so we rearrange this to solve for A, and it looks like this. And then you just plug in the values, okay? So the acceleration is 35.09 meters per second squared. So the answers are the final velocity is 220 meters per second up, and the acceleration is 35 meters per second squared up. Keep in mind, keep a note that make sure you always put in the correct units. Make sure that acceleration is meters per second squared. And again, it's talking about sig figs. I haven't really taught sig figs in this class, so don't worry too much about it. But the idea behind significant figures is that the answer, the value of the answer, the like decimal places, how many decimal places used should be consistent with your problem. When I mean consistent, it doesn't mean it should be the same, but there's various techniques for figuring out that. There's various rules. But like here you have 5.2 seconds, and you have a displacement of 5.7 times 10 to the, which would be 5, this is like 570. Okay, because I don't want that. How do I get rid of that? This right here is 570. So if you have that, an altitude of 570, having an acceleration of like, an acceleration with too many decimal places, like 35.09032, that's not, you don't need that level of we don't know the answer that precisely. Okay, using the equations of kinematics, what is the initial velocity of a car that reached 32 meters per second south in 3.4 seconds at a rate of 2.6 meters per second squared? Notice the units on this. What is that? This is our acceleration. Okay. The initial velocity that reached, okay, it's asking, okay, for V1. It gives you the delta T, right? That's right here. And this, notice the units, again, meters per second, that's going to be our V2. Because what is the initial velocity of a car that reached? So reached is kind of like your final. Okay, so given that, we draw it out. We have our initial velocity we don't know. Our final velocity is 32. Our acceleration is 2.6. And we look at our equations to see what's going to work for this. Okay. And so here we can use this equation. We can rearrange it to solve for V1. You plug it in, and you get the answer of 23.16 meters per second. The initial velocity of the car was 23 meters per second south. Okay, example 4. Pause this video and see if you can solve it for yourself, and then follow along. Okay, a cruise ship can accelerate at 0.01 meters per second squared. If it starts from rest, how long does it take? How long does it take to reach a speed of 25 kilometers per hour? Notice here, what do you notice? That this, it's a speed, right? It's given in kilometers per hour. And here, our acceleration is in meters per second squared. How long would it take if it started from a speed of 2 meters per second? Okay, so what do we know? We know that the acceleration is 0.01 meters per second squared. We know that it starts from rest. Okay. It's asking for how long would it take. And it's telling you that the final speed or final velocity. Now it doesn't say. Notice that here it doesn't give a direction, and here it doesn't give a direction. It gives you a speed. Okay. And so this is 25 kilometers per hour. So here, just recapping, this is all the information that you're given, right? Now here, we need to convert our V2 into meters per second. And so here we have 25 kilometers per hour. We need to convert the kilometers to meters. So there's 1,000 meters per kilometer. And you can see when you do this that the kilometers cancel with that. And you're left with meters, which is what we want on the top. And then we multiply it by an hour over 36 seconds. And what that does is it cancels hours here, and you're left with seconds. So then you're left with meters per second, which is what we want, which is ours. Okay, so we end up having a V2 of 6.94. So no direction is given, so assume forward is positive, or you can get rid of the vector hats and say that, okay, we're solving this without direction. We can use this equation, rearrange to solve for delta t, because it's asking for the change, how long it takes, okay? And then you plug it in, and your result would be 11.57 minutes. Oh, excuse me, 694.4 seconds, but that's really large, and so obviously we'd want to make that a little bit more attainable. Like, what is 694 seconds? It's hard to think what that is. So you can convert that into minutes by multiplying it by 1 minute divided by 60 seconds, and you get 11.57 minutes. That's a little bit more meaningful. Okay, next example. Oh, excuse me, this is part 2. Let's go back to our equation, our problem. So that was part 1, was solving for this. Part 2 of this problem says, how long would it take if it started from a speed of 2 meters per second? So for part 2, they're saying, okay, everything is the same, but now our V1 is going to be 2 meters per second. So basically we do the same thing, but we start with here, we add this. Instead of subtracting 0, we subtract 2 there, because up here we subtracted 0 here, and now we're subtracting 2. And so we get this 494, and we need to convert that to minutes, and it ends up being 8.24 minutes. Okay, to recap, you draw a diagram. It helps to visualize the situation. It reminds you to label positive and negative directions. Then you write out the values. It helps to see what you know and what you need to find out. And it makes it easier to determine which equation to use. For choosing the equations, you choose the equation based on what you know and are looking to find. Have your equation list handy. If solving for 2 unknown values, always try to solve for the second unknown value without using the first. General tips: look for keywords from rest or to a stop. Check that all the units match. Rearrange before subbing in. If the question does not indicate units, use logic. Thank you for watching.